All right, welcome back. So today we're going to discuss the idea of trig integrals and sort of put into context a bunch of things related to it. I probably should first start over here on the right to remind ourselves of trigonometry. Perhaps it's been a while since we've sort of thought too concretely about these things. So when it comes to trigonometry, from some point of view, these are objects that relate to right triangles. From another point of view, a more robust point of view, these are ideas that relate to measures in a unit circle. So a unit circle is just a circle of radius 1 centered about the origin. So we've got radius 1 here. And, well, the equation that would define such a circle would be x squared plus y squared equals 1. That's sort of like an application of the distance formula. Essentially, every point that would solve that would be a point that would be exactly 1 unit away from the origin in distance. And then what we do is we take each point on the unit circle of the form x comma y, and depending upon the angle that it is located above the horizontal axis to the right, we'll establish that x comma y to be of the form cosine theta comma sine theta. So cosine theta is just the x coordinate associated with an angle theta, where theta is being measured in radians from the positive x-axis up. And when we measure the angles in radians, remember, so the positive x-axis would be measure 0, the top here would be pi over 2, and then on the left pi, down at the bottom 3 pi over 2, and all the way back around 2 pi. A radian is essentially corresponding to the length of the arc around the unit circle. And so, well, all the way around the unit circle is 2 pi, because 2 pi r, radius is 1. Okay, but I've said enough there. Now, what you can do with this defining equation of the unit circle, x squared plus y squared equals 1, and the form of every point on the unit circle, x, y, of the form cosine comma sine, is just insert cosine for x and sine for y, and get what is referred to often as the Pythagorean identity for trig functions, which is cosine squared plus sine squared equals 1. This is a classic. This is something that you should definitely know if you don't know it already. Ultimately, you're just taking cosine comma sine and plugging it into the x squared plus y squared equals 1 equation, defining the unit circle. How we will often use this when we deal with trig integrals, which we'll talk about in a moment, is we essentially solve for sine squared and solve for cosine squared. So we might want to think about these alternative expressions. All we're doing there is solving for sine squared, just subtracting cosine squared from both sides, or solving for cosine squared by subtracting sine squared from both sides. Now, another form of a Pythagorean identity that relates to sort of the canonical Pythagorean identity, cosine squared plus sine squared equals 1. If you divide both sides by cosine squared, dividing cosine squared by cosine squared gives you 1. Dividing sine squared by cosine squared, remember tangent is sine over cosine, so sine squared over cosine squared would be just tangent squared, and 1 divided by cosine squared would be secant squared, because secant is just 1 over cosine, so 1 over cosine squared would be secant squared. So here's an alternative form, 1 plus tangent squared equals secant squared, also good to know if you don't have this memorized or buried in your brain somewhere yet. And in our case, when we're doing the trig integrals, which we'll talk about in a moment again, we're going to solve this sort of for the tangent squared and solve it for the secant squared. Well, I suppose technically it's already solved for the secant squared, so the secant squared equals 1 plus tangent squared is really just a restatement of this using symmetry. But then to solve for tangent squared, you could subtract 1 from both sides to get tan squared equals secant squared minus 1. So we will definitely use these. You will see this as I sort of wipe the slate clean here eventually and proceed on to other stuff. But now, what are trig integrals all about, right? Trig integrals are, frankly, a waypoint to one of the most historically important problems that led to the development of calculus. So when calculus was first developed, late 1600s, the question of planetary bodies orbiting stars in elliptical orbits was coming into play. And incidentally, the time it takes for a planetary body to go around a star is somehow related to the area swept within that ellipse over time. So if you sweep an equal amount of area, that will take an equal amount of time. So assuming these two bits of area are equal in size, then the time it would take for the planet to move from one point to the other would be of equal time. So this was an observation of Johannes Kepler dating before the 1600s, but to mathematically justify this, frankly, required calculus. Now, this may seem like a tangent, but bear with me. The formula for an ellipse, in standard form at least, is x squared over a squared, where a is just a number, plus y squared over b squared, where b is just a number, equal to 1. And if you solve this out for y to try to get a function, you have to bring the x squared minus a squared over a squared to the right-hand side. You have to multiply by b squared, and then you have to take the square root of the y. So essentially, y would be a degree 2 polynomial because this x squared would now be on the other side. So you've got an x squared term and nothing higher on the right-hand side, and that would be under a square root once you solved for y. So if you took the equation for an ellipse and put it into functional notation, you'd have the square root of a degree 2 polynomial. So this historically important situation where calculus was ultimately developed, planets going around stars, relates to a function which is the square root of a degree 2 polynomial. And in fact, we need to know areas related to that function. And so, well, we'd have to be able to compute integrals for such functions. So one goal that we will have in mind, and it's going to take probably a few classes to get to the point where we are even addressing this goal, because we've got to get through trig integrals to get to the next section, which is really directly related to this. But here's a waypoint when we talk about trig integrals. We're trying to work towards computing the integrals of functions that have degree 2 polynomials inside square roots. Historically important because this is where calculus came from. And ultimately, for us to have empathy with this history, we ought to be able to study such integrals. Well, to do so, we've got to ultimately get to trig integrals, because not unsurprisingly, when you're talking about ellipses, which are sort of like circles stretched out, it's not altogether surprising that some form of trig function might be helpful in such settings. And in fact, trig functions really provide the key to the castle in this situation. So the forms of trig integrals that we will focus on in this section so that we can ultimately get to the point of the degree 2 polynomials inside the square roots is integrals of the form sine to some power times cosine of some power, or integrals of the form tangent to some power, secant to some power. If you look at the two trig identities that we were discussing, one of them involves sines and cosines, and one of them involves tangents and secants. This is not a coincidence. In fact, we will work with these in exactly such a form. So I'm going to scrub the slates clean here for a moment. We're going to work through an example or two just to see this in action. And then, yeah, I put the ... here. There's other forms which you'll likely see through homework and classwork and whatnot. But yeah, I'll touch on a couple basic examples to get us warmed up. And then, yeah, we'll be off and running with trig integrals. All right, so let's hammer out a few examples related to trig integrals. So we mentioned that one form is powers of sine and cosine, which you see in the first two examples, and then one of powers of secant and tangent. Frankly, the first example is something that could have shown up in the section on U substitution. And as it turns out, these trig integrals are really a practice in U substitution while also dealing with trig identities at the same time. And so if you look at this sine to the fourth x cosine x dx, and we're trying to ask ourselves what function has a derivative of this, I kind of like the fact that I've got the sine function inside a degree 4 function, right? Because one way to interpret this sine to the fourth is you could think of this if you wanted. I'll just sort of rewrite this slightly. You could think of this as sine to the fourth, right? So now we've got a function inside a function. This is classic U sub territory. So what would we want to set u equal to? Well, the inside function of sine x. And if you set u equal to the sine of x, then you can compute derivative, right? Du would just be cosine x dx, which actually takes perfect account for that extra little bit that's hanging out on the right. So the cosine x dx plays the role of our du, whereas the sine x plays the role of our u. And so our u is our sine x. So piece this all together using substitution. Replace the sine with u, you'll get u to the fourth. Replace the cosine x dx with du, and hey, this is ready to rock, right? This is 1/5 u to the fifth plus c. But of course, we don't leave our answer in terms of u because the original function was stated in terms of x. And so we simply replace u with sine x, and so we'd have 1/5 sine to the fifth x plus c. So Not too shabby, right? Nothing too complicated here in some sense. This was really just a manifestation of u sub. We required no trig identities to resolve it. However, what about this next example? This next example is actually quite related to the previous example. I kind of like the fact that I've got the sine function inside my raised to the fourth function, but different from last time, instead of just having a single cosine, we've got 3 cosines. But here's the deal. If we've got 3 cosines, we can actually chisel away 2 of those cosines using the identity cosine squared equals 1 minus sine squared. If we chiseled away 2 of those cosines, we'd be down to just a single cosine, and then the du could take care of that. And that is, in fact, our exact strategy. Frankly, anytime you have an odd power of sine or cosine in such an integral, we can resolve it using the tactic that we're about to employ. So if you have an odd power, set the one that's not the odd power equal to u. So we'll have u equal to sine x. If u is equal to sine x, then compute the derivative. Du is equal to cosine x dx. Okay, and now, again, cosine x dx leaves 2 cosines unaccounted for. If we apply u substitution, we'll have integral of u to the fourth times cosine squared x times du. Because one of the cosines and the dx replaces with du, leaving 2 of the cosines left over. The sine to the fourth is just u to the fourth. We've got that properly accounted for. But if we're going to integrate this new function that's now in terms of u, we're going to have to get x out of the integral. But we can get x out of the integral because cosine squared is just 1 minus sine squared. But wait a second, 1 minus sine squared would be just 1 minus u squared. So here's the idea. We're going to replace cosine squared x with 1 minus sine squared x. And 1 minus sine squared x can then be replaced with 1 minus u squared. So put this all together, we get u to the fourth times 1 minus u squared du. And boy, I wish there was a product rule for integration that would make life so easy, but there isn't. However, we can just use a polynomial product here to rewrite this as integral u to the fourth minus u to the sixth du. And then when we integrate, well, we'd get 1/5 u to the fifth minus 1/7 u to the seventh plus c. But of course, we don't leave our final answer in terms of u's. We're going to write it in terms of what u is, sine x, right? Because our original function was in terms of x. It'd be kind of silly to write our answer in terms of u's. So what I'll do actually, just to save a step, rather than writing out 1/5 u to the fifth, I'll just write 1/5 u is just sine x. So that would be sine to the fifth x, and then we'd have the minus 1/7 sine to the seventh x plus c because we just computed an indefinite integral. But there we are. There's our result for our second example. So where the second example was more sophisticated than the first, whereas the first was just able to yield to u substitution, the second required u substitution with an additional application of a trig identity. But with one application of the trig identity, we ultimately got ourselves to a form where we could work this out. It's actually kind of a similar story in this bottom case. Think about the tangent and the secant whenever you take derivative. If u is equal to tangent, then du would be secant squared. But there'd still be 2 secants left over, but actually that's not a problem because 2 secants left over can be taken care of by a trig identity. So okay, what are we going to do? We're going to let u equal to tan x. Letting u equal to tan x take derivative, you'll get du equal to secant squared x dx. And of course, secant squared x does not take into account both of those secants, all 4 of those powers of secant, but so be it. The 4 powers of tangent will be taken into account. We'll have 2 powers of secant left over, and then the 2 powers of secant otherwise, and the dx combined to be du. How are we going to deal with that secant squared? Well, we're going to utilize our trig identity to replace the secant squared with 1 plus tan squared. That's just from the right hand of the slate here. And then put it all together. Replacing 1 plus tan squared with what it would be in terms of u, that's 1 plus u squared. We'd have integral u to the fourth times 1 plus u squared du. No product rule for integration, but so be it. You can just use a polynomial product to get yourself a polynomial expression which is frankly very nice to compute with. And let's see, taking two steps at once here, because u is tan x, 1/5 u to the fifth would be 1/5 tan to the fifth. This is actually going to look real similar to the last one. And then 1/7 tangent to the seventh will ultimately resolve the situation. So yeah, trig integrals, they are a waypoint to a future section where we're computing derivatives of degree 2 polynomials inside of square roots. But for now, it's essentially a manifestation of u substitution through the lens of the utilization of trig identities. And hey, this gets us off the ground and gets us working towards a historically significant problem related to the birth of calculus.